This is going to be a short introductory video on rooted trees, mostly because the next video has so many definitions. Yeah. Anyway, so rooted trees are very similar to free trees. Basically, we just choose a root and we introduce, here, there's two things, right? We choose a root, and here for rooted trees, spatial organization matters. So one of the big things we said for graphs is that it doesn't matter how you draw this. It doesn't matter where things are. For rooted trees, it does. Absolutely. Okay. So this is kind of the rare exception. And it's nice. It gives them like a little added structure of location. So rooted trees, the spatial organization is going to matter. And all we do is choose a root. And you can visually think about this. Let's think about gravity again. And again, free trees, we didn't think about gravity. That's why it's floating. But rooted trees, we can think about gravity. I'm pushing this metaphor a little too hard. But think about gravity and imagine if we just pick up. We just grab node A and we pick it up and all the other nodes like flop down, right? What is it going to look like? So we could do that by saying, all right, node A is now being plucked. What's hanging from node A? Well, F and B are hanging from node A. They still have the same edges. And then there's nothing hanging from F, but B has C hanging from it. And then C has E and D hanging from it. And this is one way of making a rooted tree. And it's the same tree, it's the same graph as this free tree. Right? Graphically, it has the same edges, it has the same nodes. Mathematically, they're the same. But from an application standpoint, we can do different things with this rooted tree over here with A as the root. All right, so what I want you to do is now also look at what would happen if we created a rooted tree with C as the root. Okay, so pause the video, draw what you think the rooted tree of C as the root will look like. And again, it doesn't actually matter which one's the left node here and which one's the right node. It will matter in the future when we talk about binary trees, but it doesn't matter now, just for general rooted trees. So if you created one with C, again, you just think of grabbing C. That's now our root. What's hanging from C? E, D, and B. And again, it doesn't matter left, middle, or right for just general rooted trees. And then B has A hanging from it, and then A has F hanging from it. So again, graphically, all three of these trees are the exact same tree, but from a rooted tree's perspective, they are not. So hopefully I graphed these right, but yeah, looking over them, they look pretty good. This is what rooted trees basically are. So one of the nice things about rooted trees is actually inherited from just any trees. So any tree, right, there's only one path connecting any two nodes. And that's still the case. But specifically what we think about for rooted trees is, and one of the things that's really nice, is there's only one way to get to the root, which is, again, an easier property to have because there's only one way to get to anywhere. But yeah, there's only one way to get to the root, which is really nice in a lot of these applications. If you think of like the directory or the paths, I don't know all the words, but like on your hard drive, right? You have, like C ... // all right. I'm embarrassing myself now, right? But like the file locations, right? Those are rooted trees. If you're in a folder, there's a lot of places that you can go. But if you're going up a folder, right, you're only coming from one way, I think. Anyway, so we have that. If you think of like an organizational chart for like a business or the military, right, at the top you'll have your CEO, and then you'll have, maybe that's node A, and then you got VPs right over here. Maybe this VP doesn't actually do anything or oversee anybody. I don't know. If you think of like AI chess programs, their decision making can be thought of as rooted trees for deciding what to do, because these are non-greedy algorithms, right? Think of playing chess with a greedy algorithm. The elo would probably not be very high. Okay. Although maybe that's how you play chess. I don't play very much chess, but pretty sure greedy algorithms would be very bad for chess. So you can think about that. Some other examples is a lot of object-oriented designs, with their inheritance hierarchies. Those are going to be rooted trees as well. So that's basically just a short introduction to rooted trees. We have about 12 definitions in the next video, but I'm pretty sure you could guess most of them. More on that next time.